In the previous examples, we manually generated our features. We analyzed the data, we visualized it, we look at it, and we decide, okay, let's go ahead and generate this feature. That's a manual process. Let's see if we can go ahead and automate this process. Let's see if we can use machine learning models to help us out. Use machine learning models to construct features for some other downstream machine learning model. Let's talk about the idea of ensemble models. Ensemble models just refers to models that are going to use more than one estimator in its decision making. One common ensemble model is a random forest. In future lectures, we'll delve deeper into random forest, but a random forest is a collection of decision trees. And not only is it a collection of decision trees, ideally is a collection of diverse set of trees. So trees that look different, that were trained on a different data set. And the whole point here is, let's see if we can exploit the idea of wisdom in the crowds. Let's say I want to predict what will be the economic forecast in the next year. And my approach is, I can go ahead and talk to my friends, people who share my opinions, share very similar opinions to me, but that's going to be a bit biased. I'm not going to get a diverse set of opinions. So what I should go ahead and do instead is ask a wide range of people. People who are more optimistic about the markets, and perhaps more people that are pessimistic or reserved about their projections of how well the markets will do in the coming year. If I'm able to field a wide set of diverse opinions, I can take all those opinions and make the best judgment. That's kind of what's going on here when we talk about ensemble models, something like the random forest. If each decision tree in this forest is different, so it's diverse, then I can go ahead and pool all those predictions and make a prediction that overall is better than just using a single individual prediction from each tree. Okay, so let's go ahead and try out random forest. We're going to import from Ensemble, import the random forest regressor. We'll use grid search. We're going to scale our data. In the random forest, like I've always stressed before, let's go ahead and look at the documentation, see what's available for us to tune this random forest. So one of the key hyperparameters for random forest is the number of estimators. This tells you the number of trees that make up this forest. So it looks like the default value is 10. So we can go ahead and do a grid search and tune. In this case, we're doing max number of features. This will make sense when we go more into decision trees, but this is choosing how many features should I consider when I'm splitting, when I'm making those node splits, when I'm constructing each individual tree. So this might take a while. The reason this is going to be slower to train is because notice I have 50 estimators. So I need to train 50 models at the same time. Remember, what I'm trying to do here is I'm trying to construct a diverse set of opinions from all these trees and pool that answer. Okay, it's going to take a while, so I'll just go ahead and move on. Other hyperparameters I can tune with the random forest are the min samples leaf. How many samples, what's the minimum number of samples that can make up a leaf, a terminal node in my tree? So this will prevent the growth of my tree. And I can also tune the number of estimators from my model. How many estimators should I use for my ensemble? Of course, using more models will in general be better, but what will be a consequence of using too many estimators in my random forest? Any consequences of having a very large forest? What do you think might happen if I have a very large forest? In other words, I have a lot of different models I need to train every time I'm trying to train a random forest. Well, if the random forest is very large, then it's going to be really slow to train. It's going to be really slow to train. That's going to be a problem. Something that might happen is that there might be a point in which adding more trees isn't going to really help out the overall model. For example, let's say I've asked 50 economists, and I get a pretty good set of opinions, and I can ask 100 more economists or 50 more economists for 100, and perhaps their opinions they're sharing me aren't that different than what I already have. So I'm asking more and more economists what their opinions on the forecast of the markets for the coming year, but the answers they're giving me aren't any more different than I already have. So it's not going to really really change my overall opinion, my overall prediction I'm going to use based upon what all these economists told me. So in fact, sometimes when we're working with the random forest, if we have some sort of error metric here, some sort of metric of error, what we'll see is we increase the number of estimators, the number of models, the number of trees that compose the forest. We'll see a sharp drop, but after a while, it kind of plateaus, and it kind of might bounce around a bit, but it kind of flattens out. So there really is no need to go beyond this number. Like I said, these models are a bit slow to train, as you can see here, so we'll just go ahead and move on. So that's one type of ensemble model. We can go ahead and create our own custom ensembles. And this is great because hopefully by now I am comfortable working with scikit-learn, so I can be able to make my own custom estimators. And what I want to do here is very similar to what's happening with random forest. Perhaps I'm going to use one type of machine learning model. Let's say decision tree or random forest. And then let's say I want to use another model. Let's say k nearest neighbors. And both these models predict different values, right? They're going to behave differently. They're going to perform differently. So they're going to predict different values. But what I want to do is I want to take the values they predict, and I can treat those as features. I can treat that my machine learning models, in this case, some sort of decision tree and a k nearest neighbors, as generating features from the raw data. And those features are their predictive values. And I can take those predictive values and figure out what's a good way to blend them together. This is called a blending ensemble. And this is in contrast with the random forest, in which we bag all the answers. We aggregate all the answers from each tree. That's a type of ensemble model. It's a bagging model. So let's go back to what I was discussing here. So we have raw data. It's going to come in. Here comes my raw data. And one goes to maybe k and n. Out comes out its predictive value. So I'm going to call this yk, representing the predictive values from my k and n model. But at the same time, I trained and I'm making predictions from a decision tree. So here comes the predictive values from the decision tree. Now I can treat these. I can go ahead and generate a new feature matrix in which one column is the predictive values from one estimator, in this case k and n, and the other column are the predictive values from the decision tree. And now I can take this new feature matrix and pass it on to another machine learning model to learn what's a good blending of these two predictions. Yes, one naive approach is I can go ahead and just sum them all up, average the predictions. But what do you think I'd be doing there? What do you think would be a problem with that approach if I simply just average out the predictive value from k and n and the predictive value of decision tree? It might be that maybe one of these models does better than the other. Let's say in this case, KNN in general does better than decision tree. Then would I really be making use of that information or making use of that behavior that one model does better than the other if I simply average out the results? No, if I simply average out the results, what I'm implying is that I'm equally weighting these two models. I'm saying these two models do just as well, so I'm going to average them out, treat their predicted value to have equal weight. But that's not always the case. One model might be better than the other. So because of that, what I need to do is I need to blend them by considering one model might do better. So that's why I can view what I'm doing here is I can take these predicted values and put them into a new feature matrix. So essentially, what I can do is I can say the overall predictive value can be a blend of one model's predictions. Let's say this is model 1. I'll just go back to the convention of k that I used here, plus alpha of d, y of d, where these are weights, which tell you how much I should emphasize one model's predicted value over the other. Now the question is, what should be these weight values? What should be the value of alpha k and alpha d? These are simply coefficients, weights. What should be these values, and how should I figure them out? So one way to view what I'm trying to do is I'm trying to figure out what are a good set of alpha k and alpha d. And I know what y of k is and y of d. Those are the values that come out of the KNN and decision tree model. What does this equation remind you of? What does this equation remind you of? Where have we seen something similar to this before? Well, this is analogous to saying my predictive value is some coefficient times my feature 1 plus some coefficient times my other feature and so forth. In this case, I only have two features. So you can view here is I have a linear regression framework. I have a linear model. So perhaps I can use a linear regression model to learn what is a proper blend from these two models. What's the best way to blend the two predictive values? How much weight should I add to KNN? And how much weight should I add to decision tree model? That's why it's important that I need to take these two predictive values, put it into a feature matrix, and pass that on to something like a linear regression model. In other words, my workflow could be, here comes my raw data. Here comes KNN. Here's KNN here. Predicts its own value. Here's the decision tree. This gets grouped together. So this is sort of x of t. And this gets fed into, let's say, linear regression. It doesn't have to be linear regression. It can be something more complicated, but nonetheless, it's some machine learning model that's going to take the predictive values, view them as features, and figure out how to use those to make a better overall predictive value. So looking at here, so going back to the idea of feature engineering, feature extraction, we've simply done this feature extraction, feature engineering process automatically. We're using these models to generate new features. So looking at this workflow, that's a little bit complicated. At least it's not a simple two-step process that we've seen before. So guess what tools we're going to use to create this blending estimator, this blending ensemble model. What tools are we going to use? So we're going to make use of feature unions and pipelines, because we can see here We can go ahead and convert this into a transformer and this to a transformer. We want to combine, unionize these two predictive values. So we have feature union there, and then we can go ahead and encapsulate the entire process into a pipeline. So let's do this in scikit-learn. Let's go back to the notebook. So that's what we'll do here. What we're going to go do here is that, remember, these machine learning models, KNN and indigent tree, yes, they are regressors, but we want to use them to generate features, to be transformers. So we got to be able to construct a custom transformer that wraps around the models, how the model makes predictions. In other words, we want to create a transformer that's going to take the predictive values and use them as features. So that's what we do here. The way that this custom transformer works is that we have to pass it an estimator. We have to pass it a machine learning model that it's going to use to generate features. During the fitting process of this transformer, we're going to simply fit that estimator that we passed it. But for the transformation process, we in fact want to use the predict method of the estimator, of the predictor. So that's what's happening here, because remember, those features that we generate are the predictive values from that specific model. So that's why we're going to use the predict method. You might be wondering, what is this np at least 2 function? Let's go ahead and practice looking at documentation. So what this function does, it's a nice way to automatically generate a 2-dimensional array if we pass it some other array. So we see here we can pass it a scalar like 3. And what I'll do is I'll go ahead and convert this into a 2-dimensional array. So we take the shape, and sure enough, it's a 2-dimensional array of 1 row and 1 column. Let's say we do something else, like let's say I'm going to use the arange function to generate a 1D array of size 5. So if I look at this, if I look at the shape, it has generated a array of 1 row and 5 columns. But we want to go ahead and instead generate an array of n number of rows in 1 column. So that's why we can take the transpose. The transpose just means you're going to take the rows, become the columns, and the columns becomes the rows. So that's why we do that one last thing of taking the transpose. So this right here, we'll reshape it into a new array of 1 row and n number of columns, where those n's are the number of observations, and we simply take the transpose, and we have our data set in the right format. We have an array in our right format. So let's go ahead and run this here. Now it looks like this finished running. I won't run the rest, but you get the idea. Okay, now let's go ahead and construct our model. So we have one pipeline that's going to scale our data, and it's going to have our k nearest neighbor regressor. We want to tune that model. So that's what we're going to do there. We're going to tune the number of neighbors, which is a key hyperparameter of the k nearest neighbor model. Right, this might take a while. But notice I'm tuning it. I'm tuning the model. Let's see how well it performs. So let me talk about what's happening here. Is that we're going to construct 2 different transformers. This estimator transform based upon decision tree regressor, and one based upon the k nearest neighbor regressor. And then our workflow is we scale the data, and then we pass it to this ensemble. We call this ensemble. And then we pass it to linear regression to learn how to best blend the 2 models. And here we set fit intercept to false, because if we look at our framework, well, I already erased it. We set there was y hat is, I'm going to use beta 1 times model 1 plus beta 2 times model 2. So there was no intercept in this equation that I wrote out. So we can go ahead and set intercept equals false. So hoping now we can see an example of the power of pipelines. And notice, let's see how well our model performed. So using k nearest neighbors, just using k nearest neighbors, it had an R-squared value of about 0.72. But if we take two estimators that are going to generate features from our original data, our raw data, those features are its own predictive value, and train a linear regression model to best blend or learn how to best blend those two models' outputs, then our model's performance has increased. Now we have an R-squared value of 0.73.